In this video, we're looking at sample proportions lesson 7.3, but before we do that, we're going to look at a sort of an activity. I'm going to do some of these with you. Some of these you're going to work through in your group of 5 today. So let's see if we can get through this together. So first of all, we have a large bag of Reese's Pieces that has about 1,000 pieces. The manufacturer says that exactly 40% of the candies are orange. If we select a sample of 50 pieces, how many will be orange? Now first we're going to let x be the number of orange candies in the sample, and then we're going to explain why x is a binomial random variable. So binomial meant we needed to be binary. We needed to have independent trials. We needed to have a fixed number of trials and the same probability of success. Alright, so binary, our success is orange, our failure is not orange. Independent, we have no replacement, but 50 is less than 10% of 1,000, so that counts. Our number of trials, we have 50. The probability is always going to be 0.4. Alright, now on Teams there's going to be the link to this applet so that you can actually try this. And using that applet, we're going to take a random sample of 50 pieces and we're going to record how many pieces were orange. And we're going to repeat this 5 times and write our values in the space below. So your values are going to be different than my values. When I ran this, I got 14, 23, 18, 24, and 15. Now what you're going to do with those 5 values, one of you, or share the values among each other so that we can create a dot plot of our sampling distribution of x. I can only put my values on there because I don't know what values you're rolling. So my dot plot is going to look slightly sad here, but it'll be okay. So yours should have 30 dots on there, my 5, and then 5 for each of you. So yours should be much nicer. We can still do the rest of these though. So what does each dot represent? So each dot is one sample of 50 candies and counting the number of orange. Now we have to find the mean and standard deviation for the binomial distribution. So our mean is n times p, which if we do the mean for this here, that means we have 50 times 0.4, which is 20. Our standard deviation, we have the square root of n times p times 1 minus p, which means we have the square root of 50 times 0.4 times 0.6, which is 3.46. And with that, we want to find the approximate shape of the sampling distribution of x. So first, we gotta check our large counts principle. So our n times p needs to be greater than or equal to 10, and n times 1 minus p has to be greater than or equal to 10. So 50 times 0.4 is 20, which is greater than or equal to 10, and 50 times 0.6 is 30, which is also greater than or equal to 10, which means we're approximately normal. We have a normal curve with a mean of 20 and a standard deviation of 3.6. Put our curve there, label our mean. There we go. Alright, instead of finding the number of candies that are orange, we will find the proportion of candies that are orange. So use your 5 samples from number 2 and turn each number of orange candies into a proportion. So again, your numbers are going to be different, but from number 2, let's just use mine as an example. I had 14, so 14 out of 50, which is the same as 0.28. 23 out of 50 is 0.46. 18 out of 50, 0.36. 24 out of 50, 0.48, and 15 out of 50 is 0.3. What did you do to the number of orange candies to turn them into proportions of orange candies? We divide by 50. So hopefully you were able to do that with your own numbers and get decimals for your own numbers. Now once again, your sampling distribution, share your numbers among each other, make some sampling distributions on your papers. You should have 30 dots on your papers when you're done. So I had the 0.28, we had a 0.46, we had a 0.36, a 0.48, and a 0.3. Those were mine. So make sure you get those 5 down, your own 5, and then the 5 of the 4 other people in class. What does each dot represent? One sample of 50 candies, and the proportion of orange. Now we gotta find the new mean and new standard deviation. Now our mean is n times p over n, so our mean for the proportion is just p, which means that our mean of p hat is 0.4, which was the 20 that we had before divided by 50. For our standard deviation, we've got n times p times 1 minus p over n, or p times 1 minus p over n and square root that, which means our standard deviation is 0.0692. Now we want to check if it's approximately normal with our large counts condition, which hopefully is still being met. Which it is, so it is approximately normal. Alright, so we know that the bag of Reese's contains exactly 40% that are orange. If we select a random sample of 50 candies, what is the probability that the sample proportion will be 50% or greater? So we need our normal curve. We got our 0.4 in the middle. We want to figure out that it's 0.5 or more. So we got to find the z-score of the 0.5. We had 1.45. Then we need to find our area. So we're going to do an inverse normal and get an area of this. So we have a 7.35% chance that the sample proportion will be 50% or greater. Alright, now that we're done with our activity, let's take our notes for the day. So we have our sample proportions. we're going to again divide that section into two. So we have sampling distributions of p hat, which means we need a shape. This needs to be approximately normal, which works if n times p is greater than or equal to 10 and n times 1 minus p is greater than or equal to 10. This p was our success, 1 minus p is our failure. Our center is mu of p hat, which is the same as p. Our variability is the standard deviation of p hat, which is p times 1 minus p over n. And for here, we gotta check the 10% condition if sampling without replacement. Okay. Over on the other side, we have our normal probabilities. We have our p, n times mu of p hat, comma, standard deviation of p hat, and our value over here, that's p hat. So z is p hat minus p over p times 1 minus p over n. Or you can use our old formula for z-scores, which was x minus mean over standard deviation. Both come out to be the same thing here. Alright, according to the American Dental Association, 8% of adults have never had a cavity. A dental student contacts a simple random sample of 1,000 adults and calculates the proportion p hat in this sample who have never had a cavity. So our mean p hat is going to be the 0.08. Our standard deviation is the square root of 0.08 times 0.92 over 1,000, which is 0.009. We gotta check that this meets our 10% condition. So 1,000 needs to be less than or equal to 10% times the number of adults in the U.S., which it is definitely less than that because there are millions of adults in the U.S. Next, we gotta check if it's approximately normal, so that's when we take our 1,000 multiplied by the probability of success, which needs to be greater than or equal to 10, and our 1,000 times the probability of failure, which needs to be greater than or equal to 10. Both of those work, so that means it is approximately normal. Now we find the probability that the random sample of 1,000 adults will give a result within 2% of the true proportion. So if our mean is at 0.8, we want to get within 2%, so we want to find between 0.1 and 0.06. Remember, it was a normal distribution with a mean of 0.08 and a standard deviation of 0.009. So we find our z-score for both the upper bound and the lower bound. And then to find the area, we can use our inverse normal on the calculator, put in the upper and the lower bound as these two. We get our area as this. Now, if the sample size were 9,000 rather than 1,000, how would this change the shape, center, and variability of the sampling distribution? So our shape would still be approximately normal. because 9,000 times 0.08 is 720, which is still greater than or equal to 10, and 9,000 times that is here, which is also greater than or equal to 10. Our center would still be our mean of p hat, which is still 0.08, but our variability is going to change because this time in our formula we're dividing by 9,000, which means we get 0.003. So if n is multiplied by 9, so your standard deviation is 1/3 of the original one. And that is all.